Hey everyone, Adam Savage here, and today we are stepping out of my cave to explore the technology and engineering of delivery drones. Wing is a company that uses small autonomous aircraft to do last mile delivery of small packages, like a lunch order or urgently needed supplies. Users order on an app and the package can arrive in as little as 15 minutes. It's the kind of thing that sounds like science fiction, but is already taking place in deployments all around the world. We visited the Airfield, where Wing conducts test flights, and met up with CEO Adam Woodworth to learn how these aircraft operate, how they're tested, and what happens if a drone delivery doesn't go according to plan.
In 3, 2, 1. That was it.
All right, Adam, tell me where we are in the world right now.
So you are at Wing's main test facility. So we got a couple big hangars. They're filled with lots and lots of airplanes and crates full of airplanes.
You spent your whole life building planes. Did you ever imagine you would make so many of a single model?
No, it's still, every time I walk in here, I still just look at the stacks of planes, and there's a moment where I sort of step back and the pupils get bigger.
So how long have you guys been in the facility?
It's been a handful of years now. We sort of built it out specifically to be able to do a lot of volume flying. This is where we do sort of all of our certification testing.
Right, but Wing's been around for 10 years,
Yeah.
so what did you do before you had this facility?
So this is, we did what most flight testing looks like, is either out in a desert or you're out in a big empty field.
And for some of the safety stuff you're doing, it's about logging tens and hundreds of thousands of hours of flight time, right?
Yep. So if you sort of boil it all the way back down, what we're trying to do is make our aircraft just as safe as the rest of commercial aviation.
Right.
And to do so, you need to accumulate lots of flight hours, lots of flight cycles.
And you can set up situations that you have in the real world, like parts of, one of the store vendors you're working with, you can set up what their delivery system looks like and test it here before it goes out, right?
Yeah, as you'll see outside, we've got a handful of different installations. One is set up to look just like one of the store installations we have, with the same fencing. We have like fake power lines that we installed.
For it to avoid.
So that I can see them and make sure that all those algorithms are working right. We've got a big array of pads that are just for the volume flying, so we can accumulate lots of flights in a short amount of time.
Right.
And then we've got some of our infrastructure deployed here. So like our autoloaders, we've got them set up really close to the building so that you can capture like, any GPS weirdness or shadows or things like that.
Of course.
The goal here really being to like stress test the system before it makes it out to operations. The idea of drone delivery has been around for a long time, but it's existed in that what if space. It's like, what will it look like?
Yeah.
What will hundreds of airplanes flying around at the same time look like? And you get to see bits of that here, and you get to see sort of how far the reality that we're living today is from the perception that folks have of what it might look like.
Well, and speaking of what it might look like, humans have built a very robust system for certifying things that fly. Yeah. But this is a brand new category, and I'm curious if our certification of things that fly is changing somewhat because of this industry.
And in our operations, the U.S., we're what's called a Part 135 air carrier, which is basically we're like a little airline.
Okay.
And when
amazing.
Yeah. I wouldn't have thought that when I first started this. And what that means is that there's a big stack of papers that have been written long before we existed about what it means to be a little airline.
Right.
And all the rules and regulations to do so. There's some of those that are directly applicable to the things that we do. Mm-hmm. There are others that aren't, but they're still part of that big stack of paper. So an example of this is like, you can look and check, there are no seatbelts on our aircraft.
Right.
That's because there's nobody in it. But there are lines in those regulations around like aircraft shall have seatbelts. And it's this
and there's no modifier or qualifier for that.
It's not like, unless it's a little tiny airplane. Right. So there's this whole long collaborative process. Our approach has always been like, at the end of the day, we're not going to put seatbelts on the airplane.
Yeah.
So like that's the outcome we need to get to. But we recognize that process has been around for a long time and for good reason. And so how do you sort of work together to get to the right outcome?
Every one of your planes knows what its job is and it knows how to do it, but what happens when it can't do some aspect of its job? How do you guys plan for contingencies?
Yeah, so I think that's like a core element of the approach is like defense in depth, right? So you want to have many layers of sort of contingency actions or like decisions that the airplane can make.
Yeah.
While it can still make them. So as you saw when they go and do their sort of morning checkouts, that same sort of like comparison of what it's supposed to be doing versus what it's actually doing is happening all throughout the flight.
So it's constantly checking itself.
Yeah, so constantly checking itself, and if it's up cruising around like an airplane and it's saying, hey, like I'm carrying a little bit more roll than I should, or it's requiring slightly more power than it usually does, that all gets recorded. Mm-hmm. And then if it's sort of a small enough change that can still go do the delivery, it'll go do the delivery. And when it comes back, it'll land and say, hey, like somebody should come look at this airplane. Okay. If the airplane determines like, hey, I probably shouldn't do the delivery, it'll just turn around and come back. If it's more pronounced, like, hey, I'm carrying more power than I have battery to make it back.
Which it can tell.
Yeah, which
right?
it can tell.
Right.
Maybe I should land sooner than getting back to base. And we call those contingency landings. So it's basically like the airplane, if it's cruising around like a plane, it'll slow down to a hover, mm-hmm. And it'll slowly descend down and land on the ground, like it would back at a charge pad, but just like out in a field or in a tree.
And it does this slowly.
Yep, very slowly. Think of it like a very big electronic parachute. You'll see it slows down. It gives people a chance.
It's very confidence building that it does that.
And then that's it.
Wow.
So like that's it's like basically like an electronic, like the world's, think about the size of a parachute you would need to come down that slow. And you have control over where it ends up. A couple of things there that are important to us are one, like, the airplane knows what it's flying over. Right. So we can say, hey, like if you need to land in grass or land in a tree or don't land on a road or don't land on power lines.
And it can actually tell the difference between those things. It has a map of the world.
Yeah, it has both a map of the world and the cameras on board have the ability to sort of classify those things. So it can say like tree, car, road. Our philosophy there is like, if the plane can fly, let it keep flying, mm-hmm. and let it sort of steer itself towards the safest landing spot. If you compare that to like, what if you just pulled the parachute? Like at that point, you've lost control of the sort of
the moment you pull the parachute, it might be safe, but you have no more say in anything.
Yeah,
that it
it's
does.
up about a couple hundred feet. You pull a parachute. It happens to be over a big field, but there's a big wind. It could blow over a road, or it could blow into a lake. And I think that's our approach is build a bunch of redundancy into the system so that you can both identify and sort of like take on those failures without it affecting the flight.
I'm curious if you've mucked with these to find. I kind of want to see what's the lowest number of rotors that can get it to limp back home.
Those are sort of specific things that we test for, particularly during the certification pieces. They're called likely failures and specific demonstration points. So we have to show, like, okay, you say it can fly without a motor missing a quadrant, go do it.
Oh, so you'll go tape up.
You say it can fly with the weight all the way slid to the back of the box. Like, go do it. And we go even steps further than that. We've done exercises where like people have we'll rip off a part of the wing, will intentionally fail surfaces and show that it can still maintain flight.
That sounds like a really fun day.
Yeah.
Well, one of the things that I've always appreciated about the FAA specifically is it has been an amazing beacon of the clarity that safety is not a thing, it's a process. And a constantly ongoing process. They've always allowed anonymous reporting of mistakes without punishment, et cetera. And this is amazing to see how much you go through to make sure that this thing can still get itself home. All right, we're about to see another unspectacular demonstration.
Another unspectacular demonstration, but an important one. Okay. So, we're going and delivering to people's houses, and those environments change all the time.
Yeah,
So,
yeah.
it's important that the aircraft can be able to understand what's going on over what it's delivering and adapt to that. So a common example would be you pick the delivery zone that's in your driveway and somebody happened to park a car there.
Right.
Making sure that the airplane can know that the delivery zone is clear, and if there are options to, like, deliver the package slightly to the side. If there are no options, then like sort of take the box back with it and say, sorry, couldn't deliver the package.
And this is all autonomous. No one's interfacing with the machine to make that call.
There's no like live video feedback to an operator that's like, okay, we delivered over here. It's the plane making that sort of very well-defined, bounded set of decisions of like, move it a little bit over here, move it a little bit over there.
Among the contingencies that Wing plans for is what happens if someone pulls the string before the package is released. Here, they've designed the drone to sense any abnormal tension on the line, and if needed, the drone will leave the tether behind, allowing the drone to safely fly away.
I got it! I want to talk a little bit about the difference between being breakable and being frangible. Talk to me about frangibility and your machine.
So I think the easiest way to describe frangibility is like being able to break in a very specific and controlled way. So if you think about like a car crumple zone,
right,
or like a race car hitting a barrier, the parts of the car that break to protect the occupant,
right,
those are essentially like frangible designs.
And the frangibility is a breakability that distributes the force away from where you don't want it and towards where you do want it.
Yep, and also sort of like distributes that force over time,
right?
So that sort of less of it is imparted to the occupant.
So how does that come into play with these things? If they fall out of the sky, there's a specific way you want them to break.
So yeah, I think to sort of back up one bit to
Sure.
the fall of the sky piece, this is designing around a very, 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 very rare occurrence. Mm-hmm. But an important occurrence, right? So,
right,
back to the points of like, you're designing physical things, they operate in the physical world, like they will break eventually.
Right.
They're not gonna break every day, they're not gonna break every month, but we believe that you have to plan for that outcome. And if you plan for that outcome, you can minimize the impact of that outcome. So how that works on our aircraft, you've seen sort of the ability to, sort of break different parts of it,
yep,
and have it still work. If you look at the plane, it's mostly styrofoam, sort of bits of plastic, but the sort of skeleton of the airplane is carbon fiber rods. So
gotcha,
there's these 3 roll-wrapped carbon tubes.
Mm-hmm.
You've got a slightly thicker one for the main spar, so that goes right through the wing, and then you've got these ones, and these are the motor mount pieces.
And these are slightly thinner because they don't need to
They don't have the
as much.
same, the most load you're seeing is through the wing. And you want this to be really stiff in a couple of very specific directions, right? So you basically want it to carry the loads that the airplane is generating. So you want it to be stiff this way,
right,
where the thrust loads are. You want it to be stiff in torsion, because when you give a roll command or something, you might have differential thrust on here. You want it to be stiff in bending along the main spar, but you don't need it to be stiff in axes where there are no flight loads. So if you think about like this motion here, there's no flight condition that would cause the plane to be able to need to be loaded in that way. Similarly, they don't need to be strong in this linear direction. So here is the most critical part of the whole airplane, and this is the joiner between the main spar and these booms. And you can see on this side, these are metal screws. There's a metal pin through here that provides torsion on this cap plate. On this side, there's a nylon screw and a number of peak screws, which is like a hard acetyl type.
And they're held on with some type of thread lock.
These are so like anti-rotation marks, so we would know if they backed out.
Gotcha. Okay.
And so you want this to be really sturdily attached. But if you were to have an impact on the front of the boom, or you were to have a load on the side, you want it to be able to break. So you see that.
Wow. And this is so, let's say in the worst case scenarios, this thing hits something delicate, it's taking some of the force of that hit and distributing it away. I'm grooving on your use of this mechanical thing and describing it as a fuse. I get it. Is that like a standard way of describing it from a mechanical engineering
Yeah,
standpoint?
yeah. Generally, I mean, you think about like structural fuses built into things, and it's the sort of like, you know, on like bridge beams, we want them to bend, not break. So you have some like expansion joints and things like that. And even like high sensitive components where you want to break the structure before you permanently damage it. That's the idea that's happening here. So you can see like this piece is still full intact. So you've got the sheared off heads of all those screws.
Right.
And this part is what carries all the main flight loads. That's
And it's still totally intact. You haven't damaged it. So even a broken plane still is has a bunch of usable parts. You haven't rendered it completely.
You haven't. And that's the I could take this plane and I could just push it off of this table, and if it landed in a particular direction, you'd probably break the structural fuse, but it's not meant to be loaded that way.
Right.
And so this is, you know, to take some of the analogies we've used before even further, like this, we want to build the safest plane we can. And so that starts with making it really redundant, really reliable.
Yeah.
It moves into making it be able to absorb failures that occur in flight. It means being able to assess the health of the airplane while it's flying. And then in the most extreme case, building for that sort of, you know, one in way more than a million type of problem, making sure that if it bumps into something, it doesn't break that thing.
Incredible. And you guys have a testing procedure, I believe, which is behind us here.
This is we usually have we've done a bunch of impact testing on these in like instrumented labs where you're measuring the forces, you're making sure that those correspond to with a number of like well-established like NHTSA standards.
Okay.
Like same deal they do with impact testing for automobiles. To be able to demonstrate it to you all, like we don't have one of those facilities here, but you can sort of replicate it by scissor lift and some cables.
I got to say, it feels like a very familiar setup to me.
Yes, so we thought you'd feel at home here. And, you know, again, this is a contrived scenario.
Sure.
Like, there's a reason why we're not flying to show you this, because it's a very hard thing to see in reality.
Right.
But, you know, we think it's important to show, like, you know, seeing a broken airplane does not mean that something bad necessarily happened.
Indeed.
They're sort of made so that I always say like people before airplanes. Like I'd much rather have the airplane be broken, than have sort of any harm come to anybody.
What spectacular destruction. We're about to break some airplanes on purpose, and of course we want to film this on high-speed camera to get beautiful slow-mo shots, and we're in luck because the best slow-mo guy in the world, Gavin, is right here. Hello,
Hello.
sir.
I think my favorite thing is just apparating. Whenever you need slow-mo, I'll just be there, hiding in the shade.
Talk to me about your camera. What are you going to film this at?
This is too fast for what we're doing, really.
Fair.
But I'll probably run it at 20,000 frames a second.
What?
And then we'll get this one in a bit closer, a bit wider at 2,000 frames a second.
Wait a minute.
Like
This is 2,000 frames per second, this little beautiful thing?
This is crazy. This is pretty much the exact specs of what I was shooting 10 years ago on a camera this big, but now it's...
10 years ago, in 2014, we were almost done filming the show, and we pretty much almost never filmed above 1,000 frames per second, unless it was a super special occasion. And that's like the floor for this.
Yeah.
Crazy.
Yeah, I don't think I've ever run it that low.
That's amazing. Here we go, in 3, 2, 1.
Cool. So you can see the stuff that was supposed to break broke.
Yep.
So you see we had one boom hit first, and the motion of that boom stopped. So the plane kept going.
The other boom didn't even seem to notice.
Didn't get the message yet.
Nope.
And that helps you sort of take that load and sort of dissipate it. And
Right,
same deal with the other boom hits, take that load and dissipate it. And you can see here, the wing is still, looks like a wing.
Right.
The center body still looks like center body. And, while this is a super, this is we're an extreme test.
Right, we have gone for the most damaging possible test of this thing falling.
But you could see sort of how that is engineered to break.
This thing weighs 11 pounds, and that means that what was happening here was a lot less than 11 pounds hitting that mark.
Yeah. And it's all about sort of taking those loads and distributing them over space and time.
Amazing.
Cool.
Dude, so cool. Let's crash it again.
Yeah.
Thank you guys so much for watching. I didn't want to finish this video without a huge shout out to Wing. They've designed Wing to crash safely. We really wanted to see that on high-speed camera. They were game from the very get-go, which is amazing to me because not a lot of companies want you to look at footage of their main product crashing. But Wing was on board. They were excellent partners for this video, and I just wanted to thank them.